Temperature is an important scalar property of water, usually represented by a capital T. Thus we have T equals a function of x, y, z, and t. Or in geographical coordinates, T is a function of longitude, latitude, z, and t. Here z is the vertical coordinate, noting depth, and t, little t, is time. Temperature is a critical property because it influences the dynamics of the water by modifying the density, and because temperature has a direct effect on biology, playing a role in the metabolism and growth of critters at all trophic levels. Temperature is related to the internal kinetic energy of a substance. Fundamentally, it's a measure of the thermal energy. The temperature scale used by oceanographers is Celsius, which carries the same units as absolute temperature in Kelvin, with a different zero. Now 0 Kelvin is known as absolute zero, the point of lowest internal energy, whereas the zero of the Celsius scale is approximately the point at which freshwater freezes its standard atmospheric pressure at sea level. I say approximately because this definition has changed slightly over time to be a bit more precise. Now, how do we measure temperature? There are lots of ways, but for the purposes of oceanography, we focus on techniques that can quickly reach a steady state value, having measurements that can be stored on non-volatile media and are fairly inexpensive. Now, most of us are familiar with the Mercury Thermometer. Mercury expands with temperature, and a linear scale is used to interpolate between two calibrated endpoints. Aside from the hazards of working with mercury, this technique is quite slow to reach equilibrium and is really no longer in use these days. It's also impractical to suit up a graduate student and send them into the abyss in order to record the local value at depth. To avoid the latter problem, reversing thermometers were used from the late 1800s, including the polar expeditions of Nansen, all the way up until the early 1970s. Reversing thermometers use mercury to measure the temperature, but when an established depth was reached, the thermometers were flipped over using various means, including the use of a mechanical messenger sent down the cable. Design is such that when the thermometer flipped over or reversed, a constriction cuts the thread of mercury, and any mercury that is expanded past the point of constriction is stuck in a capillary trap. This mass of trapped mercury is essentially a stored data point that can be converted to a temperature back on the ship. These reversing thermometers thus enable local depth to be recorded, and this allowed for measurements of regular depth intervals in a single cast to the seafloor from an ocean-going vessel, and thus a temperature profile at a fixed location could be established. The readings of well-calibrated mercury thermometers are considered reliable to around 1/1000th of a degree Celsius. The modern methods use thermistors, which exploit the effect of temperature on the electrical resistance of a material, principally semiconductors. The word thermistor comes from the combination of thermal and resistor. These devices are cheap, rapidly reach equilibration, and are amenable to digitization. They rely on proper calibration as well as a good understanding of the relationship between temperature and the electrical properties measured, but in practice they're quite reliable and they can achieve a precision of around 1/1000th of a degree Celsius. Thermistors are point measurements, meaning each temperature log represents a single point in space and time. They can be deployed on stationary assets such as a mooring or a lobster trap, providing a continuous time series at the fixed location, or they can be deployed from a ship at a fixed site in a vertical cast. They can also be towed on sleds that move in a sawtooth fashion behind the ship, allowing for optimal sampling of the water column. Another class of deployments is the drifter, which is designed to drift with a particular patch of water while making measurements of the water properties of the patch and communicating them acoustically through the water via global satellite networks when access to the surface is possible. A fourth class would be AUVs, or autonomous underwater vehicles, which use passive propulsion such as gliders, which can modify their buoyancy, or active propulsion including both propellers and impellers. AUVs use complex navigation techniques to follow a preset course that often includes intensive vertical sampling of the water column. AUVs are becoming more and more affordable, and efforts are being made to extend their range at sea by harvesting solar and wave energy when they're at the surface. Now, everyone has seen maps like these of the global sea surface temperature. This kind of spatial coverage would be impossible to achieve using fixed thermistors. The source of this data is, of course, satellites, which means that this temperature measurement was made hundreds of kilometers above the Earth. This method of making measurements without direct contact is known as remote sensing. In the case of sea surface temperature, satellites are just simply exploiting the fundamental principle that all objects with temperature greater than 0 Kelvin give off radiation, and the characteristics of that radiation depends on the temperature of the body. The sun gives off radiation in a broad spectrum of wavelengths, and we take advantage of that using the two sophisticated spectral sensors we have in our skulls, our eyes. Satellites use advanced very high resolution radiometers, or AVHRR systems, to detect radiation from the sea surface. The raw data is sent back to labs around the world, and then complex algorithms decompose that into temperature. It seems a little pretentious to include advanced and very high in your acronym, as if nothing will ever improve on your achievement, but it is hard to criticize a technology that has revolutionized the study of oceanography. Now, it's important to note that satellites are measuring the spectrum of radiation emitting from a very thin layer on the surface of the ocean that's around a millimeter thick. This is known as the skin. The temperature of that skin can be significantly different in temperature from the water just below it, depending on the time of day, the winds, and other factors. Thus, getting from the spectral measurement to what we call surface temperature, which is the temperature of the fluid in the upper meter or so, requires a significant amount of processing. There's been a lot of effort on this topic. Aside from the obvious restriction that you're only measuring surface temperatures, remote sensing also tends to have difficulty when there's significant cloud cover, which can be frustratingly persistent in some parts of the world and can also be present at times when you need it most, for example during a hurricane. Precision for AVHRR is highly dependent on the conditions and is improving rapidly, but is typically around 1/10 of a degree Celsius. Modern instruments provide measurements at the spatial resolution of around 5 kilometers at roughly daily timescales, which depending upon the specifics of the satellite orbit. Remote sensing of temperature can also be performed using instruments mounted on other platforms, such as balloons and planes and kites. These are typically used for higher resolution studies of processes in smaller regions, like in river plumes where a cold river will dump into a warmer ocean. Temperature in the world's oceans range from around -2 Celsius to 32 Celsius. The temperature of ocean water can be negative since the dissolved salts contained within it reduce the temperature which it freezes. If we look at a global distribution of sea surface temperature, or SST, from satellites, we see a strong latitudinal variation, which is driven by the latitudinal variation of solar radiation. The equator receives more sun than the poles. The variation is not strict, however, and there's some longitudinal variation as well. At this scale, these variations are created by local differences in surface heating and cooling, strong motion of ocean currents across the globe, like the Gulf Stream, and strong vertical motion of ocean water, either upwelling, or downwelling. Seasonally, we see a shift in the warmest water from the northern hemisphere to the southern hemisphere, and if we look at the annual ranges, we see that in the vast majority of the ocean, the temperature variations are very small, just a few degrees Celsius over the year. In other areas, mostly confined to regions near the eastern side of the continents, we see much sharper annual differences which can exceed 25 Celsius in the more shallow coastal areas. These areas feature very strong seasonal weather which drive annual heating and cooling cycles that shape the temperature of the water. They also tend to be more productive biologically. Looking at sea surface temperature is interesting, but it gives a very skewed perspective on the volumetric distribution of ocean temperature. The vast majority of the ocean is cold, very cold. The average temperature is around 3.5 Celsius, and more than half of all the ocean water lies in the range from about 1.5 to 4 Celsius.